In this video, I'm describing very briefly about the multiple comparisons, okay? What does that mean and why do you need that? In a single factor ANOVA, rejecting the null hypothesis does not mean that all means are different from one another. As we discussed earlier, applying multiple two-sample t-tests to examine the difference among more than two means is not valid as it increases the type 1 error. In this section, we'll discuss process to compare k-means with each other in the single-factor ANOVA experimental design. There are many methods that is applied for multiple comparisons. We discussed some that are frequently used, especially Tukey test. Okay, multiple comparison tests are adversely affected by heterogeneous variance among the sample population. So what is happening is, if you are comparing, let's say, mean of the 3 groups or 4 groups, if you reject the null hypothesis, what that means? That means the null hypothesis will be all the means are equal, right? And alternative hypothesis means not all of the means are equal. So if you reject the null hypothesis, meaning that you will say not all of the means are equal, but it doesn't tell you which mean is different from which one. It does not give you anything. But this is the, we also call post hoc test, meaning that after you reject the null hypothesis in the ANOVA, in one way ANOVA, then we want to know which of the mean is the different from the other means. Okay, so we want to compare each first mean and second mean, first and third mean, first and fourth mean, second and third, second and fourth, in that way we want to compare mean of each of those combinations. That is the multiple comparisons. Okay, we also call post hoc test. Okay, let us see. If there are k samples, then there will be k times k minus 1 over 2 pairs that we can compare. If all samples have the same size, Tukey test, also known as honestly significance difference test, is an excellent way to compare the means if they have the same sample size. To apply this method, we need to arrange the number of all sample means in ascending order first. Then we find the pairwise difference between the means xi bar minus xj bar. So first of all, you need to find out the mean of each of the group, and then you compare those means. Okay, then we find the test 2k test statistic will be xi bar minus xj bar over se, standard error, where se is under the root se square over n, and se square is equals to se square w is the mean square error defined in ANOVA. So we use exactly the same mean square error for se square. Okay, to find the critical value, we use the Q distribution table for 2k test with n minus k and k degrees of freedom and alpha. For H0, it is Hi equals to Hj. We reject H0 if Q is greater or equals to the critical value. So here I have discussed the way how to do it manually. Okay, but usually we use R to find out that. Okay, that's why I'm going it very quickly. So what are the steps? Let's write down the steps. H0 is mu b equals to mu a. Okay, so you will be doing the pairwise comparison of all the possible pairs actually in the ANOVA. Okay, if you reject the null hypothesis, then you will be comparing all the possible pairs, and H1 is mu b not equals to mu a, where mu a is the mean of sample A and mu b is the mean of sample B. To find the test statistic, we find the mean of each sample and sort them in ascending order. Then find the pairwise difference of the means and find the standard error. S equals to S square over N, where S square is also called S square W. Actually, we wrote SSE there. Okay, so we wrote SSE. That is the SSE. That's how we denote in the ANOVA. So not SSE. Actually, this is the MSE. Okay, where this S square W I denoted is the MSE, mean square error. That, how do we denote that? Mean square error was defined by SSE, sum of square error divided by the degrees of freedom, right? That's what we were denoting. Defined in ANOVA. Finally, find the test statistic Q equals to xi bar minus xj bar over standard error. That is that standard error you do. Okay, and find the critical value using the 2k Q table, and then n minus k and k degrees of freedom, and then alpha. So for H0 is equals to that, we reject H0 if Q is greater than or equals to the critical value. So that's how you use the you do manually, but we'll be using R directly. Okay, so let us read the note. 2k test can withstand minor deviation from normality, but it is less resistant to the heterogeneous variances. The test is conservative if small n is associated with the smaller variance. All right. So assumption is the observation being tested are independent within within and among the group. Okay. The group associated with each mean in the test are normally. This is like a Anova. That's why it's the same assumption from the Anova are applied here. There is equal within group variances across the groups associated with each mean in the test. So I have so let's see. So if there are unequal, that is for the equal sample size. You see that equal sample size. If there are unequal sample size, then H0 is that, so the same null and alternative hypothesis. Only SE is that the same MSE. Okay, but where SE, if so, look at this. If the two samples have equal size, this is the SE square formula. But if they have unequal size, this is the SE formula. SE square over 2, 1 over NB plus 1 over NA, where SE square is same as that SE square. Okay. Finally, find the test statistic, the same as the other one. Okay. And all these, so testing all these steps, other steps are the same. Testing all pairs of means with unequal variances. If the variances are not equal, then we use SE equals to that value. SE square A over NA plus SE square B over NB, where SE square A is given by this formula. Okay, SE square A is given by where is that? That is MSE of A and MSE of B. That's what you use. Okay, and then we use in that case variance. So if you know that the two population variances are equal, use Tukey Kramer test discussed above. But if you have a doubt, then safer to use this method. Okay, so other methods for multiple comparison use are also Duncan test, student Newman Kuhl's test, Don, or there are so many other tests. Okay, so what I'm going to do is, so you can Google it for these tests. You can find out a lot of materials. What I'm going to do is I'm going to discuss only one example using the Tukey test. This is the non-parametric test for the multiple comparison, similar to the Kruskal-Wallis test for the multiple ANOVA, right? Or the for the ANOVA, non-parametric ANOVA, there is a non-parametric test for the multiple comparisons too. So you can search it again. I'm just telling you that there is this this method exists. So what I'm going to do here is I'm taking a plant growth example. What is happening in the plant growth is, in one column it is given the weights of the plant, and then in another column is the group. There are control group, and then there are treatment 1 group and treatment 2 group. There are 3 groups, right? So you want to test whether the mean of the plant growth or the weight of the plant is different among these groups, control, treatment 1 and treatment 2 groups. That's what we are doing, plant.av. That's what just analysis of variance, I just name it, which is equals to AOV is the analysis of variance, weight versus the group, right? Data is plant growth. So that's what we are doing here. If you do the summary, what do you get? You get that the p-value is less than alpha. That means the average weight of the plant is different, are not equal among all these 3 groups. Okay, the average weight of the plant are not different among all these 3 groups. Now, so we want to know, so we are rejecting the null hypothesis. That means the average is not equal, right? But which average is different from which? So which 2 averages are same, which 2 averages are different? That's why we use the Tukey HSD. Tukey test, I'm just naming Tukey.test. You can give any name. Equals to Tukey HSD is the function for the Tukey test. Okay, Tukey HSD, and then you do that function, plant.av. So it will give you the pairwise comparison. Let me do that. Look at that, pairwise comparison. So you see that treatment, if you compare treatment 1 and control, you see that p-value is greater than alpha. So they are equal. Similarly, treatment 2 versus control, this is also greater than alpha. So these 2 average are equal to, but treatment 1 and treatment 2, this value is less than alpha, meaning that we do not reject, we reject the null hypothesis, right? That means the average in the treatment 1 and treatment 2 were unequal. That's what it is causing the rejecting the null hypothesis in the Anova. So it was doing that, right? But if you want to know how does the plot look like there, look at this plot. You see that treatment 1 versus treatment 2, they are not equal because the confidence interval So is not containing 0, right? That means they are not equal. These two have the 95% confidence interval, are including 0, but this was not including. That means that they are not equal. Their average is not equal. Okay, guys. So let me read some of the notes, and then in the next video we'll be doing the two-factor ANOVA. So things to know for one-factor ANOVA. We did one-factor ANOVA the parametric way and non-parametric way, and also we did the multiple comparisons. Okay. The first one is the sample should be randomly selected. The sample size are roughly equal. In extreme cases, largest sample size divided by the smallest sample size should not exceed 1.5. That's the one of the things that we already discussed, right? The dependent variable should be quantitative. All the data must be numerical. If the response variable is our Likert scale, use the non-parametric test. In case of the Likert scale, you always use the non-parametric test. Some people argue that if the Likert scale has more than 5 options, we can use ANOVA. That's the thing you can think of. No outliers or extreme values within the groups. If there are outliers, you can replace it with less extreme values or transfer the data into another form or delete it, or proceed under the assumption that the outliers will not affect the analysis. Independence of sample. The participant in one group should only be in that group. It should not have any influence in the probability of the others, because one of the assumption of the ANOVA, we are not doing the dependent sample, we are doing the independent sample. Okay. Normality. The response variable should be approximately normal distributed with in each group. For bigger sample size, ANOVA is robust for violation of non-normality. Normality can be checked using Shapiro-Wilk test. For normally distributed population, you can transfer data or use the non-parametric test. ANOVA is robust for small violation of normality. Homogeneity of variance. If the data has severely non-homogeneous homogeneity of variance, there is chance of type 1 error. Homogeneity can be tested using several statistical methods. We did the Levin's test and Bartlett's test, right? If you do not have homogeneity, you can make it homogeneous by transferring the data into other form or declare that your data do not meet the assumption. Okay, so this is the end of one-way ANOVA. Okay, guys, thank you.